Hello guys, this is a video solution for tutorial sheet 5, which is this one. This is a tutorial sheet on R. So this is the third tutorial sheet on R, okay. So in this, through command by command, and also do there are 5 exercises at the end. I will do them, okay. All right, the first thing is this session is more about how to compute probability distributions in R. I mean, nearly every probability distribution, whether it is discrete or continuous, can be computed using R, right? But for this session, I will only talk about these 4 discrete distributions, which are binomial, Poisson, geometric, and negative binomial, and these 7 continuous distributions, which are uniform, normal, exponential, chi-square, beta, and student t. So the R name, there is a name in R for each of these distributions. So for example, binomial is called binom, right? Poisson is called poise. Geometric is called geom. Uniform is called unif. Normal is called norm, and so on. Right? So for example, if you want to compute the density of the normal distribution, right, which is the PDF of the normal, you use the command dnorm and then specify the values of x at which you want to compute the density. If you want to compute the probability, or in other words, the CDF of the normal distribution, you use the command pnorm and specify the values at which you want to compute the CDF. And if you want to compute the quantiles of the normal distribution, you use the command qnorm and specify the probabilities at which you want to compute the quantiles. And finally, the R norm is used to generate random numbers from a normal distribution. So here n specifies the number of random numbers that you want to generate, right, using this command, right? So once again, so this is for the normal, but in general, dname will compute the density, right, of the distribution specified by name. So the name can be one of these names, right? Pname will compute the CDF, right? Qname will compute the quantiles. Rname will generate random numbers from the distribution, right? N here specifies the number of random numbers. P here specifies the probabilities at which you want to compute the quantile. Q specifies the values at which you want to compute the CDF. And X specifies the values at which you want to compute the density, right? So this table here at the very end of page 1, it applies to any distribution, right? It can be one of these 4 or one of these 7 or any other distribution that you want to work with in R, right? So let's go to the next page, okay? And let me open the R session, a new session, right? Let me close this window. Right, so so let me give you some examples, right? Suppose you have a binomial variables, right? Okay, so let me use the number key. Suppose, excuse me. Excuse me, just a minute. Suppose x is a binomial random variable, right? With n is the size parameter equal to 50, and p is the probability parameter equal to 0.6. So this is just a comment. Now, if you type xb equal to a sequence from 0 to 50, by 1, right? So this gives you the numbers from 0 to 50 in steps of 1. Now, if you type PXB, right, assigned to D binom at XB, where size parameter is 50 and the probability parameter is 0.6. So what this command does is it computes the density of the binomial distribution, which is the PMF, at the values specified by XB, right, when the size parameter is 50 and probability is 0.6. So if you type PXB, these are the density values of the binomial random variable with parameters 50 and 0.6. So if you plot XB, comma PXB, you see this plot here. So this is the probability mass function of a binomial random variable with size parameter equal to 50 and the probability parameter equal to 0.6. Okay. Now this command here, dbinom with x equal to 35 and size equal to 50 and probability equal to 0.6, right? This command here computes the density or the PMF of the binomial at 35 and the size parameter is 50 and probability is 0.6, right? Okay, so, and this command here, P, well, when Q is 25, yeah, size is 50 and probability is 0.6, this computes the probability that a binomial random variable with parameters 50 and 0.6 is less than or equal to 0.25. All right, so just to, okay, maybe I should do a number key. Okay, let me do a comment. So what I have written above is the probability that x is less than or equal to 25. So, right, so this number here, 0.097, etc., is the probability that x is less than or equal to 25. Now, suppose you want to compute the probability that x is between 20 and 30, right? Okay, this can be computed as follows. To compute this, first, you compute the probability that x is less than or equal to 30 and take away from that the probability that the probability that x is less than or equal to 19, right? So this is the answer that you will get. Do you see why? Because the reason for this argument is that this probability is the same as the probability that x is less than or equal to 30 minus the probability that x is less than or equal to 19, right? Because remember, if you want all the numbers between 20 and 30, first you must compute the probability that x is less than or equal to 30 and then take away from that x is less than or equal to 19, because x being a binomial random variable, it can only take integer values, right? So that's what I have done over here, right? So you compute the probability that x is less than or equal to 30, take away from that x is less than or equal to 19, right? Right, now next are the quantiles. So if you use Q binom, you can obtain the quantiles of the binomial distribution. So for example, the median, remember the median corresponds to the probability being equal to 0.5, right? So the median for the binomial random variable with size 50 and probability 0.6 is this, right? And the first quartile, remember the first quartile corresponds to the probability of quarter, 1/4, right? So it's this one. Okay, so that's how you compute the quantile. So the third quartile corresponds to the probability of 0.75, so it's 32, and so on. Okay. Now, okay, guys. All right. That's the next thing is how do you generate random numbers from a binomial distribution? So for that, you will use the command R binom, right? So suppose you want to generate, say, 5 random numbers from binomial with size equal to 50 and probability equal to 0.6. And this is what you get. So every time you enter this, you get different numbers, because the random numbers, first time you do, may not be the same as the random numbers next time, and so on, all right? Okay, so they are different. Okay, and similarly, you can change the size, and you take size 1, right, and the probability 0.6, right, and say this time you say you want to generate 8 random numbers, you'll get this, yeah, or you get this. So every time the numbers can be different, right? Okay, now let's consider, so far we talked about the binomial. So now next, let's talk about the normal distribution, which is one of the most popular. So suppose X is a normal random variable, right? With mu is the mean parameter, as you know, equal to 0, and the sigma is the standard deviation parameter equal to 1. All right. So then you can use the command denorm. Denorm will compute the density of the normal distribution. So that is the density of the normal at x equal to 0. Right. Now, if you want to compute the density for a different value of mu and different value of sigma, you need to specify what they are. So mean, you will specify the value of mu, and ST, the standard deviation, will specify the value for sigma. So this is the density at x equal to 0 for a normal variable with mu equal to 4, sigma equal to 10. Okay. Now let me show you how to plot the density of the normal in R. All right. So the first thing is you need to define the x values, say from minus 26 to 34 in steps of say 0.2. All right. Then let me define the y values as the density of the normal distribution at xn, with mean being the mu value equal to 4, and the standard deviation parameter, which is the sigma value, equal to 10. Then if you say plot xn versus yxn versus xn, this is what you get. So as you can see, what you have here is the density of a normal distribution with mu equal to 4 and sigma equal to 10. Okay. Right now, if you want to join the line, so at the moment the way it is plotted, what you have are points. So if you want to join them up, you can use the type command. All right, with L stands for line. Right now, you see it's a smooth line instead of being points. Right. Another thing for normal, if you use the command pnorm, that will compute the CDF of the normal, right? So for example, this command here, this command will compute the CDF of a normal variable with mu equal to 4 and sigma equal to 10. Right? Right? Whereas the following command will compute the CDF of the normal with the same parameters at 4, 8, 12. So you get 3 different values. Right? Okay, next, how do you compute the quantile? The quantile function of a normal variable. So for example, if you say, suppose you want to find the quantile at probability 0.975, that is this. So here I haven't specified what mean and SD are. If you don't specify mean and SD, they are chosen to be 0 and 1 respectively, right? So that corresponds to standard normal. But if you do want to specify, so for example, you can specify to be the mean to be, in other words, mu to be equal to 4, and the standard deviation to be equal to 10. In this case, the quantile is this 23 point something, right? And similarly, you can get this. So this is the median value, which is equal to 4, which is equal to the mean. You may know that for the normal distribution, the mean and the median are equal, so it makes sense, right? Okay. All right. The next thing is R norm. R norm is used to generate random numbers from a normal distribution. So suppose you want to generate 5 random numbers from a normal distribution with mean or mu equal to 4 and sigma equal to 10. Use this command, you get these 5 numbers. So every time you type it, you get different set of 5 numbers, right? Because they are random. Okay. All right, the next thing I'm going to talk about is how to fit a normal distribution or any other distribution to a histogram, right? So suppose, all right, let's create a data set. So I'm going to simulate a data set from a gamma distribution. So R gamma means generate random numbers from a gamma distribution of size 100. You may recall that the gamma distribution, you might have learned this in your probability 1 course, has 2 parameters, shape and scale. So let's take the shape parameter to be 200 and scale parameter to be equal to 2. So the data that you have simulated is this one, right? So this is the data that you simulated from a gamma distribution with shape equal to 200 and scale equal to 2. Now what I want to do is I want to do a histogram of this, right? With frequency equal to false, right? And let's take the x values for the histogram to range from 280 to 500, right? So this is the x lim here stands for the limits of the x-axis. So the lower limit of the x-axis is 280, the upper limit is 500. So this is what you get. You can see here. So this is the histogram of the simulated data from a gamma distribution, right? Now, what I'm going to do is I'm going to fit a PDF on top of it, and I'll show you how to do that. Right. The first thing to do is to generate a set of x values, which I call xv, from 280 to 500. It's say in steps of 0.5. Okay, so these are the xv values, right? There are too many of them. Then I'm going to create an object called yvg, right? Which are the density of the gamma distribution at at xv with shape parameter equal to 200. Remember, we took the shape parameter to be 200 and scale parameter to be 2 when we simulated the data, right? So this is by VG. And then I'm going to do a lines command, right, of xv versus yvg with line type equal to 1. LTY stands for line type, right? So if you do that, this is what you get, you see. So as you can see, the gamma PDF, right, the fitted gamma PDF, it fits the histogram pretty well. I mean, that's what you would expect anyway, because if you simulated something from a gamma distribution, you would expect the PDF to fit the histogram well. And that's what you see here. Right, now suppose we want to fit another distribution to the simulated data. And let's take that to be the normal, right? So I'm going to compute the density values of the normal at xv, where the mu parameter is taken to be the mean value of xm, right? And standard deviation is taken to be the standard deviation of xm. So here I'm trying to fit a normal density to a data set that was simulated from a gamma distribution, and we will see how it looks like in a minute. All right, so I'm going to use line type equal to 2. You see, it looks pretty close. It looks pretty close to the, so line type 2 corresponds to a dashed line, so it's not continuous, as you can see. But it looks pretty close to the gamma PDF. So you can see for this simulated data, right, the normal and the gamma PDF approximate the histogram equally well, right? Okay. That may not be the case in general, right? But for the example that we just looked at, both distributions, the normal PDF and the gamma PDF approximate the histogram equally well. Okay, all right. The next thing, so that kind of completes the commands. Let's go back to the tutorial sheet. So this is now what I'm going to do is I'm going to go through the 5 exercises. So the first exercise, you have x, which is a binomial distribution with parameters 100 and 0.3, and the question is to find these guys: the probability x equal to 33, the probability that x is between 28 and 34, and the probability that x is less than 38. And let's see how we can do that. So you have, so this is exercise 1. So you have a binomial with parameters 100 and 0.3. The first thing is we want to find the probability that x equal to 33. So to use the command d binom, right, at 33, right, the size parameter equal to 100 and the probability parameter equal to 0.3. So this will give you the probability that x is equal to 33. Okay. Now to compute the probability that x is between 28 and 34, right? First, you must write this probability as follows: as the difference of these two, right? You see that because x is a discrete variable, can only take integer values, this probability is the same as the difference of these two, right? So now we can say that the right-hand side is equal to p binom at 34, the size equal to 100, and prob equal to 0.3 minus P binom size equal to 100 and prob equal to 0.3. So this is the answer to the probability that x is between 28 and 34. Right, and finally the probability that x is less than 38. So you want the probability that x is less than 38. Now this, because x can only take integer values, we can write this as the probability that x is less than or equal to 37. Right, so this is the same as P binom, right, 37, size equal to 100, probability equal to 0.3. Sorry. So this is the answer to the probability that x is less than 38, right? So we've done the first part. Let's go back. The second part is to use a normal approximation, which we did not cover in the course, so I will skip that. Let's go to exercise 2. So here we have a variable x that has the Poisson distribution with parameter 10. The first thing we want to do is to calculate the PMF of x at these points, right? And plot them, right? So let's see how we can do that. So the first thing you must do is to define the values from 0 to 25 in steps of 1. Right? So this is what you have. Right? Then you need to compute the density of the Poisson distribution at the values with the parameter lambda equal to 10. Right? And then you should plot xp versus pxp. This is what you get. Right? Okay. So this is the probability mass function of the Poisson distribution when lambda, the rate parameter, is equal to 10. You can type to be L. If you say type equal to L, it will join them up like this. Right. Okay, guys. All right, now let's go back to the tutorial sheet. So the next thing we want to do is to compute these 3 probabilities. Probability x less than 15, greater than or equal to 8, and between 6 and 16. Right? So let's do it one at a time. So the first probability is we want to compute is the probability x less than 15, which is the same as the probability that x is less than or equal to 14. So what we want to say is P Poisson, right, at 14 and lambda equal to 10. So that's the value. The next thing we want to compute is the probability that x is greater than or equal to 8. This by the complement rule. I'm sure in probability 1 you learned something called the complement rule. This you can write it as 1 minus the probability that x is less than 8, right? Okay, and this is the same as 1 minus the probability that x is less than or equal to 7. So this is 1 minus P Poisson at 7 and lambda equal to 10. So this is the answer. And finally, we want to find the probability that x is between 6 and 16. Okay. This you can write as the probability that x is less than or equal to 16 minus the probability that x is less than or equal to 5. All right, because if it is between 6 and 16, all right, inclusive, then it must be the probability that x is less than or equal to 16. Take away, oh, sorry, I made a mistake here. take away x is less than equal to 5, right? Okay, so let's compute the difference here. So it's going to be p poise at 16 is lambda equal to 10 minus p poise at 5 is lambda equal to 10. So that's the answer for that, right? Okay, so that completes the first part. The second part is to find the lower, median, and upper quartiles of the distribution, right? Okay, so that's not difficult. So let's go back. So you have a Poisson distribution with parameter terms. So to find the lower quartile, you just say Q Poisson with probability 0.25, right? So this is the lower quartile. To find the median, you take the probability to be 5, and to find the third quartile, you take the probability to be 0.75. So the lower quartile is 8, the median is 10, the upper quartile is 12. Okay. So that completes question exercise 2. Exercise 3 is about the exponential distribution. Calculate and plot the PDF of x for x between 0 and 25, and then compute these probabilities and also find the percentiles. Right. Okay, let's see how we can do that. It's not really difficult. So first of all, to plot the PDF of exponential with parameter 0.2, you need to define the x values. So let's call it xe, the sequence from say 0 to 25, say in steps of 0.2. Then you need to compute the density of the exponential. So let's call it d xe, d exponential xe with the rate parameter equal to 0.2. And then you plot xe dxe, right? And this is the shape of an exponential PDF, right, with rate parameter equal to 0.2. Now, once again, you can use type equal to L to have a line plot that will look like this, right? Okay. The next thing is we want to compute the probability that x is less than 12, right? So this is the CDF of the exponential at 12, right? Okay, so because exponential is a continuous distribution, it doesn't matter whether x is less than, it's the same as x is less than or equal to, right, for a continuous random variable. So this will be px at 12, the rate parameter equal to 0.2. So that's the answer. The next thing is we want to compute the probability that x is greater than 3. Compute the probability that x is greater than 3. And this, as you know, can be written as the probability that x is 1 minus the probability that x is less than or equal to 3. So it will be 1 minus p exp at 3, 0.2. So that's the answer. So that's the answer for the probability that x is greater than 3. And next, we want to find the probability that x is between 4 and 20. This you can write as the probability that x is less than 20 minus the probability that x is less than or equal to 4. Right? So you can compute it like as follows: the probability at 20 minus the probability at 4. All right, so this is the answer. This is the answer to the 3 probabilities. Now let's go back to the question. So that's part 1. Part 2, we want to find the 20th, 50th, and 80th percentiles of the exponential distribution. So that you use the QX command. So to find the 20th percentile, you put probability equal to 0.2, right? And the rate parameter is also 0.2. So that's the 20th percentile. To find the 50th percentile, you put probability equal to 0.5. To find the 80th percentile, you put probability equal to 0.8. So that completes exercise 3. Now exercise 4 is about the normal distribution with mean parameter equal to 20 and standard deviation parameter equal to 7. All right, so it has three parts, right? First part is asking you to plot and calculate these probabilities. So let's see how we can do that. So to plot the PDF, first you need to define the x values. So say xn, say from the sequence from 0 to 40 in steps of 0.2. All right. Okay, and then you need to define the PDF of the normal distribution. So you use the denorm command at xn. The mean parameter is 20 and the standard deviation parameter is 7. So that computes the PDF of the normal distribution at the values xn. And then you say plot xn comma p x n. So this is what you get, right? Once again, you should use type equal to L for line. You will get a line plot looking like this, okay? All right, the next thing we want to do is to compute the 3 different probabilities. The first is the probability that x is less than 17. So to compute this, you just say P norm 17 with mean equal to 20, standard deviation equal to 7. So that's the value. Next thing, we want to compute the probability that x is greater than 25, which you can write as 1 minus the probability that x is less than or equal to 25, right? So this you can compute by 1 minus p norm at 25 with mean equal to 20, standard deviation equal to 7. And next, we want to find the probability that x is between 13 and 27. This you can write as the probability that x is less than 27 minus the probability that x is less than 13. Right, so you can write the right-hand side as, remember, for a continuous random variable, less is the same as less than or equal to, and greater is the same as greater than or equal to, so there's no difference. So the right-hand side can be computed as p norm at 27 minus p norm at 13. So this is what you get, right? So that completes the first part of question 4. The second part is to find the 5th, 10th, and the 5th, 10th, 90th, and 95th percentiles of the normal distribution. All right, so use the command. For that, you will use the command qnorm. So qnorm, to find the 5th percentile, you take the probability to be 0.05. So that's the 5th percentile. To find the 10th percentile, you take the probability to be 0.1. And to find the 90th percentile, you take it to be 0.9. And to find the 95th percentile, you take it to be 0.95. All right, so that's part 2. Part 3, can you express these percentiles in terms of the percentiles of the standard normal? Yes, you can. Well, To do this, to do part 3, you need to know the following fact. I think I might have talked about this in the lecture notes. At least it must be in the lecture notes, that if you have, all right, let me use the command key. Suppose x is a normal random variable with mean equal to mu and standard sigma equal to this, SD equal to sigma, right? Then you must know this. You did this in probability 1, I don't know, right? Then the pth percentile of x, right, is equal to, can be written as mu plus sigma times the pth percentile of the standard normal random variable. You might recall this or not, I don't know. I mean, so what I've written here is, let me rewrite this one more time. The pth percentile of the variable x, which is assumed to be normal with parameters mu and sigma, is equal to mu plus sigma times the pth percentile of the standard normal. So I'm going to use this fact to recompute these guys here, these 4 guys, right? So for the first one, right? For the first one, our mu is 20, so 20 plus sigma is 7, right? Times Q norm of the standard normal. Standard normal mean is 0 and standard deviation is 1. So you don't need to specify that. You will get this, and this is the same as what we got here, right? And for the second, you just change the probability to be 0.1, which is the same as what I got here, okay? For the third one, you change this to 0.9, and this is the same as what I got here. And finally, you change this to 0.95, and this is the same as what you got here. So this is another way of computing the percentiles of any standard, any normal variable with parameters mu and sigma, is to use this fact here, right? Okay. So that completes exercise 4. Now exercise 5 is to basically, there are 3 data sets. I think we talked about these 3 data sets before: the simulated data, the Giese data, and the anorexia data, right? Now for each of these data sets, we want to fit a normal PDF on the histogram, right? Okay, so let's try to do that. Okay. So we will start with the simulated data first, right? So this is the simulated data. So let's go back to the let's go to the website, the course website, which is this one. So this is the simulated data. All right, let's copy the URL. Okay. And paste it here. Right. So then I'm going to use the read table command. Header equal to true, and let's call this sim data, right? Okay, now what I want to do is I want to do a histogram of this, and then on top of the histogram I want to fit a normal PDF, right? Okay, so the first thing we want to do is to do a histogram of the sim data. with remember the sim data you may recall from some time ago that it has these columns, and the column that we're interested in is this column here, which has X as the label. So sim data $x will give you this data, right? So we want to do a histogram of this data. Okay, with frequency equal to false, and I want to take the limits of the x-axis to go from 4 to 18, and the limits of the y-axis to go from 0 to 0.25. So this is what you get, right? Right. So this is the histogram of the simulated data. Right. The next thing I want to do is I want to fit a normal PDF. To do that, first I need to define the x values. So let's define them to be a sequence from 4 to 18 in steps of 0.2. Right, and then you compute the normal PDF at XS, right? So you use denorm at XS, right? With the mean, remember there are two parameters for normal, I'm sure all of you know that. The mean parameter is estimated as the sample average. So it's basically the mean of the simulated data. And the sigma parameter is estimated as the sample standard deviation. Excuse me. All right. So this is the fitted PDF values are contained in YXS. Right, finally, you use the lines command to plot the PDF, and you see this. You see, so it looks like the normal distribution is a good approximation to the histogram, right? To the histogram. Right? So that's the first part of question exercise 5. Second part is to repeat the same thing for the Giese data. Now, Giese data is something we looked at earlier. So let's go back to the website. Here we are. This is the Giese data. It has 3 columns, but the column that we are interested in is the duration column, is the duration of the eruption. All right. So copy the URL and paste it here. The table header equal to true, and let's call this Giese. All right. So we want to do something same as before, right? So the first thing we want to do is to do a histogram of the data, right? So Giese, as I said before, it has 3 columns, and the column that we're interested in is the duration column, right? So we pick out, excuse me, we pick out the duration column that we are interested in. So we want to do a histogram of this column. So it's hist of this, frequency equal to false. I want to choose the x limit, the values of the x-axis to range from 0 to 7, and values of the y-axis to range from 0 to 0.6. So this is what you get, right? Right. The next thing I want to do is I want to plot on top of this a fitted normal PDF, right? So to do that, first thing we need to define the x values. So So suppose xg is a sequence from 0 to 7 in steps of 0.2. And suppose y xg are the fitted normal, the values of the fitted normal PDF, so in other words d norm at xg, with the mean parameter taken to be the mean of the data, which is at duration, right? And the standard deviation parameter taken to be the at duration. So this, oh, there's a mistake. Oh, excuse me. What did I do? Sorry, that should be SD, guys. My apologies. So it should be SD, not DD. Excuse me. So these are the fitted values of the normal distribution for the data, right? Now to plot, you just simply use the lines command, xg, y, xg. Once again, I'm making too many mistakes. It should be lines. So this is the fitted normal distribution to the duration data. As you can see, the fit is not very good. The fit is, so this suggests that the data, the duration data, is probably not maybe some other distribution which is different from very different from the normal distribution. Could be a good model to the user data, right? Okay. All right. So that completes the second part of exercise 5. And the third part is to do the same thing for the anorexia data, but in this case, you may recall the anorexia data has it has 3 treatments, right? So we need to do it for each of the treatments, right? So let's go to the data site, the website, and let's look at the anorexia data. So you see here, the data that we're going to look at is the differences between the weights for 3 different treatments. There's 1, 2, 3 different treatments. And we're going to look at the distribution of the differences in the weight for treatment 1, for treatment 2, and for treatment 3, right? And do the fitting for each one. Okay, so first of all, let's read the data. So here we are, sorry. So copy the URL and paste it here. So this is read.table, header equal to true. Call this anorexia, ANOREXIA. So this is the data. Now we want to create 3 different data sets corresponding to the 3 different treatments, right? So first of all, let's create the differences in weight, which is the difference between the weight after the treatment, which is post weight, minus the weight before the treatment, which is pre-weight. All right, and then I'm going to create 3 different objects. So let's call it diff1. Diff1 is the differences when the treatment treatment is equal to 1. Okay, and let's call it diff2. The differences in weight when the treatment is 2, and diff 3 are the differences in weight when the treatment is 3. Right now, I'm going to do the histogram for each of these objects and fit a normal PDF and see how they look like. Right, so let's start with diff 1 first. So I do the histogram of diff 1, frequency equal to false. Let's take the limits of the x-axis from the range from minus 25 to 30. And let's take the limits for the y-axis to range from 0 to 0.08. Okay, so this is the histogram. Sorry, excuse me. This is the histogram of the differences in weight for treatment 1, right? Okay, I'm going to plot on top of this the fitted PDF under the normal distribution. So the first thing I need to do is to define the x values. Let's call it xd1. Well, let's call it xd. There's no need to call it xd1. Taken to be a sequence from minus 25 to 30 in steps of 0.2. Well, sorry, what did I do? Oh, sorry, there's a mistake here. Excuse me. Right, so it's a sequence from minus 25 to 30 in steps of 0.2. Then I will compute yxd, right, to be the values of the density of the normal distribution at xd, with the mean equal to the sample mean of diff 1, which is mean of diff 1, and standard deviation equal to the sample standard deviation of diff 1. Right, then you do the lines command, xd, y, xd. Right, you see this is what you get. It looks, the fit is not really bad, but you wouldn't say it is perfect, right? So this is for the treatment 1, and you do the same thing for treatment 2. So treatment 2, you repeat the hist command with diff 1 replaced by diff 2, right? xd is the same, so this is the histogram. yxd, you change diff 1 to diff 2, and then you do the lines command. So this is the fit for the second treatment number 2. Again, the fit is not perfect, yeah, but it's not really bad, right? And finally, for diff 3, change diff 2 to diff 3. Here you change diff 2 to diff 3, and then you do the lines command. So this is the fit of the normal distribution for the differences in weight for treatment 3, right? So again, I mean, looking at it visually, it's really difficult to say whether the fit is good or not. But one of the things you will learn later when you come to doing the course, the R coursework, which is due on the 22nd of April, is that there is a way you can actually test. There's a way to actually test if a fit is reasonable or not, right? And if you look at the R coursework, which is on the course website, it tells you how to do that. Okay, so this completes exercise 5 and also completes the this video solution for tutorial sheet 5.